Okay, so in this video, we're going to discuss LeChatlier's principle. LeChatlier's principle um, allows us to look at a reaction that is at equilibrium and to see how that reaction changes based on an external force that we call a stress. So once a system reaches equilibrium, it will maintain that equilibrium unless there is a stress or a change in the environment of that reaction. And so some examples would be if we had a change in temperature or pressure, or a change in concentration, meaning we have added or removed some of our reactants or products. And so when the system experiences a stress, it has one of two choices. It can shift in the direction of the reactants, so to make more reactant, or it can shift in the direction of the product to make more product. And so we're just going to look at some examples of how this works and different ways to assess those changes. Okay. So the shift occurs to reestablish equilibrium, to get back to that equilibrium position. So any change in the concentration, remember these square brackets mean concentration, of a reactant or a product, or a change in temperature, or a change in pressure or volume will cause a shift. And I say pressure or volume because remember, especially with gases, pressure and volume are very closely related. So think about it in terms of if I had a container, right, a closed sealed container, and if I squeezed that container, right, if I squeezed it and increased the pressure, I'd be decreasing the volume, which means everything inside of that container now has less room to move around. And if it's gases, that means those moles have less space to move. And if I were to be able to take that container and stretch that container and make it larger, my volume would increase, right? But that would also make my pressure decrease because now those particles have more room to move. So pressure and volume are synonymous. They are opposites, right? When volume goes up, pressure goes down. When volume goes down, pressure goes up. But their effect is the same thing, and they will affect gases. Okay? And we'll talk a little bit more in depth about why pressure only affects gases as we go. So let's look at our first reaction and see what we've got going on here. So I have a balanced chemical equation where I have carbon as a gas, oxygen as a gas, in a reversible reaction with carbon dioxide as a gas and a heat term. And it really does not matter what the heat term is. You just need to identify where it is. And also the units could be a lot of different things. Kilojoules per mole is one. You could see kilocalories, you could see calories, but anything that is the numerical value there is going to be my heat term. So we're just going to dive right in and we'll kind of just assess as we're going. So the first thing that I want to talk about is what I've done here is I've given you a big chart, and a chart has all the possible questions I could ask. I could also take a particular row of a chart and just write one question instead of asking you about all the possibilities. This chart is just a very succinct way of addressing a lot of different things all at once. Okay? So the first thing we're going to do is when I am changing concentration, so any of these things where I'm adding and removing, I am looking at the effect of adding carbon to my system. So I cannot assess what the system is doing in response to carbon because that's the thing that I'm changing from the outside. So I'm going to mark off all of the columns that correspond to the particular change that I am making at that time. It just makes it easier if I go ahead and do that right from the beginning. All right, so let's just start working our way through this. So if I add carbon, so I'm going to add a source of carbon, which is on the reactant side. Now, the only way for the system to account for the added carbon is to use it in whatever reaction that carbon is a reactant. So our carbon here is a reactant in the forward direction. So to mitigate the addition of carbon, we're going to shift to the right and produce more product, right? So that'll allow the amount of carbon to return to normal, and the amount of carbon dioxide goes up to compensate. But what we're doing is we've essentially, if you think about it like a teeter-totter, right? We're like this, and when the carbon decreases and the CO2 increases, doesn't that level back my teeter-totter. So I see that my shift goes to the right. I see that the amount of carbon dioxide goes up. Now, what happens to the amount of oxygen? Remember that it requires both carbon and oxygen to make carbon dioxide. So if I'm making more carbon dioxide, I'm having to use oxygen. So the amount of oxygen temporarily is going to go down. And then K. Remember, K is also the same thing as KEQ, is my concentration of products over reactants. And from our discussion about KEQ, remember that KEQ is only going to be affected by a change in temperature. A change in my reactant and product concentration is not going to change it because my ratio is going to maintain itself. And so we have no change. The only time we're going to see a significant change in K or KEQ is with temperature. All right, let's go on to our next one. So if I add oxygen, well, same thing. I'm adding a reactant. I have more of this reactant. So it's going to push me in the direction of making more products. So I'm going to shift to the right. The amount of CO2 is going to go up. Consequently, the amount of C goes down because remember, both C and O2 are required to make CO2. And again, because this is not temperature, there will be no change in K. All right, let's talk about what happens when we remove one of these things. So if I remove C, okay, I take some of this away, my reaction needs to replace it. Well, the only way to replace it is to take the carbon dioxide, to push us in the reverse direction, to break down carbon dioxide into oxygen and carbon. So I'm going to shift to the left. The amount of carbon dioxide is going to go down because I'm breaking it down to make more carbon and oxygen. And the amount of oxygen goes up because remember, we're not just breaking down the carbon dioxide to make more carbon. We have to make carbon and oxygen. So that's going to go up. And here we experience no change in K again. All right, if I remove oxygen, same idea. I've gotten rid of some O. The only way to make more is to shift in that direction. So I shift to the left. The amount of carbon dioxide goes down because I'm breaking down the carbon dioxide. The amount of oxygen and the amount of carbon are going to go back up. So we're going to be able to replace the oxygen that was removed and we'll make more carbon. And no change again in K. All right. If I add CO2, so now I've added my product. Well, think about your teeter-totter again. If I add my product, I'm shifted this way. How do I get back level? I'm going to have to use the product, make more reactant, and level back out again. So I'm going to shift to the left. The amount of carbon and the amount of oxygen are going to go up, and there'll be no change in K. If I remove CO2, what do I need to do? Well, I need to make more. So how do I make more? I go hard in the forward direction, and that means that I'm going to use both carbon and oxygen to make carbon dioxide. So the carbon and the oxygen go down, and then there's no change in K. Okay? So let's talk about temperature. So you can think about temperature just like we did these reactants up here because your temperature is a reactant. In the forward direction, it's product, but in the reverse direction, it's a reactant. And so I can just think about it as adding and removing more temperature. Now, we do know that that will have an effect on KEQ, but first let's address what happens to the rest of the reaction first. So if my temperature goes up, it's like I'm adding heat. How do I get rid of that? I'm going to use it in the direction it's a reactant. So I'm going to go to the left. I'm going to produce more C and O because I'm going to the left. I'm using the CO2, so that's going down. And now let's talk about what happens with our KEQ value. Well, consider in your forward direction, who are my products? My products are CO2. And who are my reactants? C and O. So if my products went down and my reactants went up, what happened to the value of KEQ? Well, it got smaller, it went down, so K goes down. Another way to look at it is whatever happens to the products will also be what happens to K. All right, temperature. So if the temperature goes down, it's like I removed some heat. How do I replace it? I shift in the direction to make more heat. So I'm going to shift to the right. The CO2, because it's also on the right, is going to go up, and the C and the O are going to go down because I'm using them to make CO2. What happens to K? What happened to my products? My products go up, K goes up. Okay. For pressure, so some things to keep in mind about pressure. Pressure can only affect gases. Why can they only affect gases? For pressure to be a factor, your substance has to be compressible. And remember, with your gas molecules, because there's all kinds of empty space, they're compressible. Solids are not compressible, liquids are not compressible to any significant amount. So only for gases are we looking at pressure. When dealing with pressure, it's kind of similar to what we talked about with entropy. You need to think about the number of moles. So let's see, on my reactant side, I have 2 moles. On my product side, I have 1 mole. So when my pressure goes up, think about what happens to the volume. The volume goes down, which means now I have less space for my molecules to move around. So if I have less space for my molecules to move around, it would be more advantageous to be in an arrangement with less moles. So if the pressure goes up, you shift to the side with less moles. So in this case, we'd be shifting to the right. As I shift to the right, my CO2 goes up, my C and my O go down, and because it's not temperature, there's no change in K. All right. And if my pressure goes down, I can have more space because my volume has gone up. I'm going to shift to the side with more moles because I can have more things bouncing around. So I'm shifting to the left. C goes up, O goes up, CO2 goes down, no change in K. All right. So let's look at another example. All right. So this time, my heat term is on my reactant side. I have XEF4 gas, XEF2 gas, and F2 gas. So I still have an all gas scenario, and we're going to run through our various changes that we can make. Again, before I start, I'm going to mark off all of the ones that I am artificially changing so that I don't accidentally assess something I shouldn't be able to assess. All right, so let's go through it a little bit faster than we did with our previous example. If I add XEF4, so I'm adding something to the reactant side, I need to push it to my product side. So I'm going to shift to the right, and my 2 products are going to go up because when I shift to the right, my products go up. And what happens to K? No change because it's not temperature. All right. If I remove some of this, what's my shift? Okay, if I remove it, I'm going to shift to replace it. So I'm going to shift to the left. What happens to the XEF2 and the F2? Well, they're both being used to make this, so they should go down. And then there's no change in K. All right. If I add some XEF2, so if I add XEF2, the only way to get rid of what I've added is to use it. So I'm going to use it in the direction it's a reactant, which is going to be pushing me back to the left. The amount of XEF4 is going to go up. And the amount of F2, remember, is going to go down because I have to use both of those things together to make this. So no change in K. If I add F2, same thing. I'm going to have to shift to the left to use the amount of F2 that I've added. The XEF4 goes up, the XEF2 goes down, and there's no change in the value of K. If I remove some XEF2, how do I deal with that? Well, if I've removed it, I need to replace it. So I'm going to shift to the right in order to replace it. I'm going to break down the XEF2 as I'm shifting to the XEF4 when I'm shifting to the right to make XEF2. So the XEF4 goes down and the F2 also goes up because remember, I'm going to make both of these when I break that down. No change in K. If I remove some F2, I've got to replace it. The only way to replace it is to break it down, the XEF4 down to make more. So I'm going to shift to the right. The XEF4 goes down, the F2 goes up, and no change in the value of KEQ. Okay. What happens if I increase the temperature? So temperature is on the reactant side. If I increase the temperature, I have to shift in the direction that's going to use that temperature as a reactant. So if this goes up, I'm going to shift to the right. I'm going to make more of my products, and my reactant is going to go down. Now, what happens to K? Well, my products went up, so K goes up. Okay. If my temperature goes down, well, now I need to shift in the direction that's going to release more heat. So I shift to the left. The XCF4 goes up. The XCF2 goes down. The F2 goes down, and K goes down. All right, pressure. So remember, the first thing I need to look about with pressure is what substances do I have up here? What are the states of matter? Everything's a gas, so I'm good to go looking at pressure. How many moles on the left? 1. How many moles on the right? 2. Now, just hypothetically, say it was 2 and 2. If it was 2 and 2, would changing the pressure have any effect? No. Why? Because there'd be no advantage to shifting in either direction because it's the same. But that's not the case here. We do have 2 different sets of moles. So pressure goes up. Pressure goes up. Is it more advantageous to have 1 mole or 2 moles? Pressure goes up. That means volume goes down. It's more advantageous to have 1 mole. So I'm going to shift to the left. XCF4 goes up. XCF2 and F2 both go down, and no change in K. And then if I decrease the pressure, that increases the volume. It's more advantageous to have 2 moles. Shift to the right. The XCF4 on the left goes down. The XCF2 and the F2 both go up, and no change here. Okay. So let's ask a follow-up question here. What would happen if a catalyst was added? Would I have a shift, and would I have a change in KEQ? So think about what a catalyst does. When a catalyst acts on a reaction, my reactants and my products stay at the same energy position, and all that happens is I reduce my activation energy. But my reactants and my products don't change. So would there be a shift? No, there would be no shift. The only thing that would happen is I would achieve equilibrium faster, but it's still just achieving equilibrium. So there'd be no shift, and there would be no effect on KEQ because why? Well, did I change the temperature? No, just added a catalyst. I lowered the activation energy. I didn't change delta H. So the amount of heat either required or generated hasn't changed. All right, last one. No, I didn't draw the straight lines. Hold on one second. Let me put my straight lines in so this is easier for us to see. All right, so let's look at our reaction. H2 or C2H2 solid yields 2H plus AQ and 2C plus AQ. Ooh, all right, not gases. So we need to talk about what this is representing here. Okay, so let's ignore all of this for just a second. Let's just talk about this. I have a solid, and it's breaking into ions. Sounds like it's something that's dissolving, right? Like sodium chloride, salt, when it dissolves in water, makes my ions. So I have a solid dissolving into ions, but it's telling me that it's at equilibrium. So what does that mean? So you need to think back to when we were talking about solutions and specifically solubility curves. All right, so remember that your solubility curve, you had number of grams and degrees Celsius on your solubility curve, and then you had these lines. And we talked about that if I was on the line, I was a saturated solution. If I was above the line, I was supersaturated. And if I was below the line, I was unsaturated. What this is telling me, being at equilibrium, is that for sure I have a saturated solution. So think about what that means. That means that the perfect amount of solid has dissolved at this temperature. No more, no less. If I added any more solid at this point, I would become supersaturated, right? So that means any additional solid would just sink to the bottom of my beaker or my test tube or whatever I have. And so at this perfect knife's edge of a saturated solution, I have just the right amount. Okay. So if I shift in the direction of the solids, what I would see would be a solid that precipitates out of solution. It wasn't there. I added reactant. It shoved it in this direction. It precipitated out. That solid could then eventually dissolve back. But you can see some things appear and disappear when you're dealing with a solid to aqueous ions equilibrium. All right, so let's cross out our parts and we will run through this. All right, so first, if I add C2H2, well, what did we just say? That's my solid. If I add more solid to my perfectly saturated solution, what happens? Sinks to the bottom. So it doesn't cause a shift and it doesn't cause a change in anything because it's not dissolving, right? It's not adding to the ions over here. It's just sinking to the bottom. So if I add a solid to my saturated solution at equilibrium, there's nothing that happens to my equilibrium reaction. Just sinks to the bottom. All right. Add C+. So really what I should have probably written here was a source of C+, because I generally just don't have ions hanging out in a beaker. But I'm adding some C+. All right, so where does that push me? Well, if I add C+, and it's on the product side, it's going to shift me back to the reactant side. So what does that mean? Well, it means I'm going to start to cause some C2H2 to precipitate out of my solution. So I should see at the bottom of my test tube or beaker a solid start to form. So the amount of C2H2 goes up, and that's going to mean the amount of 2H plus goes down because it's being used to make the solid. No change in K. All right. What about if I remove some 2H plus, right? If I remove some H? Well, if I have any solid sitting at the bottom of the beaker, now it can dissolve because I'm going to push my reaction to the right to replace what I had removed. So the amount of C2H2 goes down, and consequently also the amount of C plus goes up because as this breaks down, right, don't I make both of these? And no change in K. All right. Increasing the temperature. Well, temperature over here on my product side. So if I increase the temperature more over here, it's going to send me back that way. So I shift to the left. What happens to this? It starts to precipitate out of the solution. So it goes up and my two ions go down. Well, this is temperature. If my products go down, what happens to K? K goes down. All right. If I decrease the temperature, what's going to happen? If I decrease the temperature, I've got to shift to the right to make it go back up again. So I shift right, the amount of C plus and H plus are going to go up because the amount of H2S is going to go down. So that goes down, this goes up, this goes up. If my products go up, remember that K goes up. All right. Pressure. Pressure. Can pressure have any effect here? Think about what I have. I have a solid. Solids aren't compressible. I have aqueous ions dissolved in a liquid solution. Liquids aren't compressible. Pressure has no effect. No effect, no shift, no change. Pressure is not a factor here. Okay. And this is a good time for me to bring up the fact that what do you do if I have, say, a solid over here and a gas over here, right? If I have a solid over here and a gas over here and the pressure would go up, doesn't matter how many moles of gas, I'm going to shift towards the gas and away from the solid. Because even though I might have more moles of gas than I have of solid, those gas moles are compressible. So pressure goes up, I shift towards the gas. Pressure goes down, I could shift towards the solid because the pressure is not going to be a factor at that point. All right. So the last thing that I have here is the addition of Li2S, or I could also put Li2S aqueous. And so we need to talk about what's happening here. First of all, number one, the first thing I should recognize is Li2S, neither lithium nor sulfur is anywhere up here. You're right, it's not. But I have to look at as I'm introducing these ions, could those ions interact with something I already have up here in a way that is significant? And the only significant thing that we're really looking at is, could they form a solid? And the reason why that's significant is, for example, if I were to form a solid with the hydrogen ions, right? The hydrogen ion concentration would go down. It's just like I'm removing H+. And so as the solid forms and falls down to the bottom of the beaker, it drags some of this H+ with it. And so now my concentration of H+ has gone down. So I'm going to have to shift to replace it. All right. Or same thing with the carbon. If I formed a solid that contained some of this carbon, it would be reducing the amount of carbon in my equilibrium, and I would have to then shift to replace it. So you have to look to see if what you're adding, even though it's not a part of this, interacts with it in any way that is significant. So I need to look at the two ions that I have potentially here. So I have lithium, Li+, and I have sulfur, S-2. Well, I'm pretty sure that this positive lithium is not going to interact with either of these in any way that's significant because they're all positive. But what about the negative sulfur? All right, so I have the potential here of making what? CS2, right, assuming the carbon's +4, and H2S. Those are my two potential products. So let's check out our solubility rules and see what we got. All right, so I'm looking for sulfides. Oh, here they are. All sulfides are insoluble except group 1A, group 2A, and ammonia. So group 1A is soluble. That means that this is soluble. That's not going to do anything. But this is going to make a solid. So what happens when that makes a solid is it removes some C. And if I've removed some C, now I need to replace it. So that means, what do I have to do? I've got to shift in the direction that allows me to make more of that. Shifting to the right, my C2H2 goes down, my C and my H would go up, and there would be no change in K. Okay, hopefully that helps.